morning. Yeah, so the last class where we had stopped off was that a system can contain a number of agents, right? And these are basically objects, and each particular object will have three attributes. That's the name, interface, and the program. Now, an object interface basically contains two sets. One is the environment predicates, and this corresponds to messages the object will accept, and component predicates that basically correspond to messages the object will send. For example, if I have a stack object, right? Now it will have these two particular predicates, that is the environment and the component predicates. Now the pop and the push, they are the environment predicates, and pop and stack full are the component predicates. If an agent receives a message which is headed by the environment predicate, then in that case it accepts it. And if an object satisfies a commitment corresponding to a component predicate, then in that case it will not trust it. Coming to illustrating it with an example, so let's consider that we have an object which is called as Snow White, right? And Snow White has some particular sweets which are the resources, and which will be given to the dwarfs, which are basically the resource consumers. And she will only give to one dwarf at a time, and she will always eventually give to a dwarf that will ask. So as you can see over here that the Snow White is being defined as an agent which is having ask, which is basically the environment predicate, and give is the component. Okay, so here we have that if the if you see this particular statement, okay, these two statements are represented by these logical expressions which is there. So she will only give to one dwarf at a time. Right? So if I represent x as the dwarf, right, then ask x and give x, okay, at a particular time only. She will eventually give to a dwarf that asks. Okay, so if I have give x and give y, okay, these are my two logical statements. Then in that case, it will be that she will be giving to one dwarf at a time. Okay, that's why it's given over here as x is equal to y. And the second statement, which is represented by this logical expression, that is, she will always eventually give to a dwarf that asks. Okay, if I have another dwarf which is eager, right, and it asks for a sweet initially, and then whenever he will receive it, then in that case it will ask again. So in this case we have eager as being the agent, which is going to have two sets of predicates. One is the environment, which is basically give, and ask, which is the other predicate, right? So if I need to write the logical statements for this particular symbol, then in that case it will be written as this, right? So it's like the eager dwarf, which is basically the agent. Okay, it asks for sweets initially, and whenever he has just received one, he asks again, right? So it's basically, so whenever he has received one, then he would be asking another. Okay, so it's like the if the agent has received it from the environment. Okay, that's the reason this has been written over here as the environment predicate, and this here we are enclosing parentheses a particular agent. Now there will be some verbs which are even polite, less polite, sorry. So they would be greedy, and they just ask every time. So it's basically ask and greedy. Okay, so they will be asking every time. So these are my component predicates, right? And the agents are passed in the enclosed brackets. Okay, and it is represented by a square box, which basically indicates every time. Okay, now there would be some particular dwarfs which would be having little manners. So there would be the courteous and they will only ask when the greedy and the eager have eaten it. So that's why these two statements are there. One is for the eager, one is for the greedy. Okay, so the cookies is not going to ask until the eager and the greedy have eaten it. Okay, so and finally we have shy, which only asks for a sweet when no one else has just asked. Okay, so they will the particular agent will ask only if no one else has asked. Right, so that's why you have to ask and you give statements. So if you only ask, then no one else has just asked it. Right? So these are my for my corresponding statements. These are basically my logical representations which are there. Now, a planning agent is basically they are the automatic programming agents, and the design of it is basically to achieve a desired goal. Now, within the AI symbolic community, it has been assumed that some form of AI planning system will be a central component of any particular artificial agent. Okay, but many planning algorithms have been proposed, and the theory of planning has been developed. We have the reactive architectures. Okay, there are a couple of unsolved problems which are associated with the symbolic AI, and these problems have led the researchers to develop architectures which are reactive. So although they are united by the belief that the assumption of underpinning the mainstream AI are in some sense wrong, reactive researchers use many different types of techniques. Okay, they do not have that that there are certain set of assumptions, and based on that only symbolic AI will be. So next what we have is we have a person by name Rodney Brooks, which defined that it's not necessary that uh, the intelligent behavior cannot be represented explicitly. Okay, so Brooks has basically put forward 3 points. Okay, that is, one is intelligent behavior can be generated without explicit representation of the kind that actually symbolic AI does. Intelligent behavior can be generated without explicit abstract reason of the kind that symbolic AI does. Right? And intelligence is basically an emergent property of certain complex systems. Now he identifies two key ideas that have informed his research. One is intelligence and emergence. So you can say that intelligence lies in the eye of the beholder, and it's not a neat isolated property. Right? And intelligent behavior arises as a result of the agents interacting with the environment. So whenever an agent will interact from the environment, it is going to learn, right? And as such, then the intelligence behavior arises. Okay. Next is the situateness and the embodiment. Now, real intelligence is situated in the world, not in the disembodied systems such as theorem proving or expert systems. Okay. So, the main real intelligence is not in proving theorems or in expert systems, but it is situated in the world. So, basically, the situation is now, to illustrate this particular idea, Brooks built some based on this subsumption architecture, and according to the subsumption architecture, it is basically a hierarchy of task accomplishing behaviors. Now, each behavior is basically taken as a rule-like structure, and each behavior will compete with the others to exercise control over the particular agent. The lower layers are basically represented as obstacle avoiding type, and they are the most primitive kind of behavior and have a higher precedence when compared to the other higher layers. Now the resulting system are in terms of the amount of computation they do extremely simple. Now we have the Mars Explorer system, which is using this particular subsystem architecture, which achieves near optimal cooperative performance in the rock gathering on the Mars domain. And here are some the typical behaviors which are there for the Mars Explorer. The lowermost layer and the most important one, and the least abstract, is the obstacle avoidance. Next is the path attraction, explore movement, as well as the return movement. Random movement is move in a random fashion, which is basically the highest layer, which is not so abstract. Now, Agri and Chapman were basically two people who have gone about building a game which is basically named as Penegi, which is basically similar to computer game with the central character being controlled using a scheme such as the one which has been defined above. Now, as we Chapman observed that they observed that most everyday critical activities are generally routines, right? So most tasks which have been already been learned, they can be accomplished easily. So he proposed that an efficient agent architecture can be based on the idea of learning the particular arguments. The idea is that as most decisions are routine, they can be encoded into the low-level structure such as a digital circuit, which only need a periodic updating. So in case if there are certain set of routine activities which the agent needs to perform on a daily basis, and in that case that can be encoded into the lower layers, right, which results in only periodic updating. Next is situated automaton. Now, sophisticated approach is basically what is there in the situated automaton paradigm. Now, an agent is specified in a rule like declarative language, and this particular specification is then compiled onto a digital machine, which basically satisfies this particular declarative specification. Now, this digital machine can operate in a time boundness, and at the time of writing, the theoretical limitations of the approach are not well understood. Now, the main difficulty appears to be that the more explicit the agent specific language, the harder it becomes to compile it. Many systems have actually argued that neither a complete deliberative nor a reactive approach is suitable for building agents. So, as we have seen before, we have deliberative approach as well as the reactive approach for building the agents. But both of them are not good. So they have suggested by using hybrid systems which attempt to basically marry the classical as well as the alternative approaches. And an obvious approach to build an agent out of the two is a deliberative one, which is basically going to contain a symbolic word symbol which develops plans and makes decisions in the way it is supposed to, and reactive, which is capable of reacting to the events without any particular complex reasoning. Now, the reactive components is given some kind of precedence over the deliberative, right? And this kind of structuring leads naturally to the idea of a layered architecture, of which the Turing machines and the interwrap are some of the examples. In such an architecture, agent control systems are arranged into hierarchy with higher levels dealing with information at decreasing level of abstraction. And key problem of such particular architecture is what kind of control framework to embed the agent subsystem and to manage the interactions between the various particular layers. Okay. So the main problem in this layer type architecture is what should we have as a subsystem among the different layers which is there. Okay, so we can say, okay, you have in the higher layer we are basically dealing with the automation, and at the lowest layer is where we're dealing with the active procedures. Ferguson basically the Turing machines architecture so consists of perception and action subsystem which interfaces directly with the agent's environment, and 3 control layers embedded in a control framework and which mediates between these particular layers. Here we have the model planning as well as the reactive layer. We have the action subsystem, and then we have a sensor input which is basically the perceptual subsystem. Right? And once the data is taken from the perceptual subsystem, then in that case it is moved to after that to the modeling layer, planning layer, and the reactive layer. The reactive layer is implemented as a situation and action view. The planning layer constructs plans and selects actions to execute and achieve the goals. The modeling layer contains symbolic representation of the cognitive state of our entity in the environment, and 3 layers communicate with each other and the underlying control framework which can use the particular control rules.